Hello! In this video, we'll extend the RISC-V multicycle processor to handle new instructions. In particular, we'll look at add immediate and jump and link, just like with a single cycle processor. So suppose we wanted to handle add immediate, or in fact any type of I-type ALU instruction. So and immediate or immediate, etc. We look at the op field. If it's got this value, then it's an I-type ALU instruction. And if it is, we want to execute it very much the same as the R-type, except the second source should come from the immediate rather than from the second register. So for this execute I-type step, the first source comes from the register file. So ALU source A needs to be 1, 0. The second source comes from the immediate. So ALU source B needs to be 0, 1 to select from the immediate. Those two sources go into the ALU. We do the ALU op that depends on the instruction. So ALU op needs to be 1, 0 to say look at the funct fields, and we get our result. And now everything else is the same. So once we've finished that execute immediate stage, then we can go to the regular ALU write back and do the same as when we were executing an R-type instruction. So now we've handled add I, but also and I's, or I, etc., all the immediate ALU instructions. And the difference was just ALU source B in the execute state. Alright, next let's take a look at adding jump and link. This is a larger change, just like it was in the single cycle processor. So remember, jump and link has to do a few things. It needs to get the J-type immediate. It needs to write the program counter for sure, and it needs to calculate the jump target address. So to get the jump target address, we do that very similar to branch. We have the old program counter. So we need to choose that with ALU source A being 0, 1. We in this step we're doing the PC plus 4. So we'd already calculated target address and decode just like we did for branch. But in this step we're doing PC plus 4 to know where to return to. So old PC and then 4. So ALU source B needs to be 1, 0. Make ALU op 0, 0 to tell it to add. So now we've got PC plus 4. Let's take that result. Meanwhile, we have the PC plus offset, which was our jump target address, sitting in ALU out during the third step. So we're going to choose that with result source being 0 and assert PC update to write the program counter with this jump target address. So that's this step. Finally, we need to write PC plus 4 to the register file, and the ALU write back step already took the output of the ALU and wrote it to the register file, so we can just use that step one more time, and result source will be 0, 0 to take the value from the ALU out, and regwrite 1 to write PC plus 4 into the register file. So that concludes our multi-cycle processor main finite state machine. Remember, this state machine takes a variable number of steps, between 3 and 5 to execute the instruction. For all instructions, we start by fetching the instruction and decoding it. Then we look at the type of instruction. If it's a load, it's going to take 5 steps. On step 3, we compute the address we want to load from. On step 4, we read a value from memory, and on step 5, we write that value to the register file. For a store, it only takes 4 steps. On the 4th step, we write to memory based on the address we computed. R-type and I-type instructions also take 4 steps. So on the 3rd step, we execute the instruction by doing the ALU operation on the 2 sources. And then on the 4th step, we write the result to the register file. And a branch only takes 3 steps, because on the 2nd step, we'd computed the branch target address. On the 3rd step, we compare the registers, and if they're equal, then we update the program counter. So that concludes our multi-cycle processor.